Okay, so sorry for the hiccups with the projector, and welcome to the first IMA seminar for the term. So it's my pleasure to introduce Dr. Shira Faigenbaum-Golovin. She's a Philip Griffith Assistant Research Professor of Mathematics at Duke University. Her research interests include mathematical modeling, numerical analysis, and robust analysis of high-dimensional data. She will talk about inferring manifolds from noisy data, non-parametric estimation, and random walks in shape space.
Okay, well, thank you for the nice introduction. And thank you, Jeff, for making this happen. So actually, Jeff and myself met last year on the JMM session that Ingrid Debussy and myself organized. And the session was about shape spaces. And there were a lot of interesting talks. One of them was that Jeff gave about classification of broken bones, that you probably heard a lot about that. And I was so excited to see his email and come and talk more about manifolds and shape spaces a little bit here. And that's what I'll be doing today. So I was thinking, what should I start with? And I decided to talk about the broader question in machine learning. Where do you first acquire the data? Where does this noisy data come from? And later I'll focus on two methods. One is non-parametric estimation of manifolds, and the other one is random walks in shape space. And I hope that by the end of this lecture, you will know a little bit both of them. And I'll also, from the broader picture, I'll try to summarize some research that I've been doing with collaboration of archaeological department and also with biological evolution. So stay tuned. So if before a lot of questions that we ask ourselves were mathematical questions and modeling that we ask ourselves were coming from physics, now more and more we see that the problem at hand that we see are coming from the data itself. We have more data that we acquire. Usually it's high dimensional or low dimensional data, and we wish to understand something about the geometry of the data, how similar or dissimilar are the data points in our collection. And we have a unique opportunity to study a question that we wouldn't have formalized if not the data itself. And we will see one of the problems today, or maybe two of them as we walk. So I'll be talking about data points, and let's denote them PJs. So our collection of data points PJs was sampled, let's say randomly, from some Rn, and we have those data points spread all over some geometrical structure, and we wish to infer the geometrical structure and say something about the global geometry that we have here. But before diving into the method themselves, I want to step one back and discuss the data itself, where those data points are coming from. And I hope that in the end of the lecture, you'll be able to answer the following questions. What if Jeff calls you tomorrow and says, oh, I have this cool application of classification of broken bones. Do you want to join? That you will be able to answer that not only by yes or no, but also where do you start from in investigation in those interdisciplinary projects like that. So that's what my goal is for today. So let's start to talk a little bit about the data, where does it come from, and then we'll dive into the manifold stuff. The data can come from maybe some evolutionary biology when we have teeth or bones, or maybe the data can come from ancient inscriptions from 600 BCE, or maybe from some artworks, that, for example, this is from Botticelli, that we wish to understand something behind the scenes of what is visible by the naked eye. So the first thing that we wish to do is to acquire the data, whether with a CT scanner or with some multispectral or hyperspectral cameras. And eventually we'll end up with a representation of, if we are scanning some objects, that we will have point clouds, and we'll have not only one point cloud, but a collection of point clouds. We will reconstruct the surfaces of point clouds and create meshes. And eventually the data will look like that. We have a collection of surfaces that we wish to investigate. If we are studying a different problem of those ancient writings, then maybe we result with those spectra that are reflected from each pixel. we wish to classify them and create some kind of shapes that represent the letters in those inscriptions. And eventually, as I told you before, we have randomly sampled data points. They're not really random, but they are related to the data in hand. And we wish to study the geometry of the data set that we have. Each point here can be either a letter, maybe some image of an ellipse, maybe some distributions, or maybe even surfaces, and we will wish to study the collection here. So what are the questions that are in our mind when we are doing that? So first of all, I told you we wish to understand how the points are related to one another. We wish to define some kind of distance between the data points. We'll be talking about that a little bit. How do we define that? Later, because we are working in this interdisciplinary project, we have some questions that the people, the experts in the field are asking us. They do not speak the math language, but we wish to translate the question that they're asking into some mathematical models and mathematical questions that we'll be able to answer. We wish to visualize the result, because that's how they know that the result is real. It will be easier for us to convince them. And eventually, we want to perform some kind of clustering, because all the questions are basically can be summarized into that. Can we distinguish between the differences in the data sets, or are they similar? So if you would push me to the wall and I would give you a recipe how to approach such data science problems with tools of machine learning, I would say that, okay, acquire the data points, and you have now high-dimensional data in Rn. You will need to perform some data pre-processing, which is denoising. Usually it's a lot of hard work, and we'll be talking about denoising and alignment today a lot. And the alignment is important because if you wish to compare two different subjects, then we have to have something that is in correspondence to one another. So we wish to somehow find the optimal transformation that those data points that we are comparing will be aligned. Then we look for the right distance metrics, which is inspired from the medium at hand. Whether we are talking about images, then we will use some prominent metric from computer vision that will measure the angles between the strokes of the letters. If we are talking about shapes, then we'll measure something else. And we will knit the geometry together. The main problem is that it's hard to infer the global geometry. So what we will be doing is basically knit it locally. For each point, we will look on the local neighborhood of that point, some kind of with a Gaussian weight. We will look on a collection of those neighborhoods. Since they coincide, we will be able to perform random walks locally, but also use that random walks in order to tailor the global geometry of the dataset. And that's what we'll be doing. And now once we have this global geometry, then we'll be able to answer the global question that the experts in the field ask ourselves. And this is basically the recipe A to Z, how you should approach such problems from my perspective. There's a lot of questions how to do each and every step here. They differ from the medium that you have in hand. And each step here can take you years to develop. And eventually we wish, I think that we all agree, to summarize the results that will influence some broader picture. We wish to publish that and get famous, because that's what we are all here as mathematicians. So I promised you to talk about manifolds. So I think that's the time that we understood where the data come from those interdisciplinary projects. And I'll be focusing first on the non-parametric estimation of the manifold, and later I will be talking about the random walks. So the first project was a collaboration with David Levin from Tel Aviv University. And it's basically, we ask ourselves, we have those data points, the PJs that was sampled, we don't know how. They sit in high-dimensional space. We do not know anything about them, but we wish to reconstruct the geometry of the data set that we have at hand. And as the title mentioned here, life is not a Swiss roll. We like to think about clear-cut examples, so examples that we can model in our methods, but in reality, the situation is much more complicated. If you have a data set that was sampled from a real application, usually you don't know how the application looks like. we have a question here. Or maybe we'll answer questions later.
We can ask him. Yeah, he said that you can
Okay.
answer at the end. Yeah.
So the data, we do not know how it looks like. We do not know even if it's a manifold. We can only assume that since we are in a regime of one application that we are talking about, that we have some kind of many underlying manifold that we can talk about. But we do not know what is the intrinsic dimension of the manifold that we originally sampled data points. What is, if it's a manifold, what is the rim? What is the representative distance between the points? We can also measure what is called the H field distances, the representative density in local surroundings. And we can try, as I mentioned before, to tailor the global geometry, but there is a lot of problems involved in that. And one of the problems is curse of dimensionality. I'm sure that you all know about that, but I'll just mention that there's a lot of problems related to approximating the data and reaching a reasonable approximation rate in terms of how many points we have. So because usually we can't sample enough points in the high dimensional domain that we have, the approximation order that depends on the density, which is here, the H, is not good enough for any practical reasons. So in order to overcome that, one approach is to do dimension reduction. So I will not go into details into every method that exists out there in dimensional reduction. There are a lot of them, but I'll just mention the key ideas that you should think about when performing dimensional reduction. This is a Swiss roll that is projected or embedded into low dimensional space via PCA, isomap LLE, or diffusion maps, and so on and so forth. We will be talking about diffusion maps a little bit later. And I have nothing about dimensional reduction. I'm doing it myself, but it's kind of risky. You don't know what the geometry is. You don't know what is the intrinsic dimension. You're projecting the data to some domain, and you hope that you reliably represent this Swiss roll. You unfold it reliably. But as you can see, even on this very simple example, it's not always true. And in reality, since you don't have any kind of ground truth, anything that you can compare and measure whether you are right or wrong, it's hard to know whether you unfolded it correctly. So dimension reduction is great, but you are making assumptions on the data. You may lose some information while doing the projections. You can do it, but do it carefully. So let's define for a minute what a manifold is, and then we'll be talking about reconstructing the manifold. While performing dimensional reduction, as I said, is nice, what I'll aim to do is reconstructing the manifold itself, the data points, on the high dimensional space. So I'll try to perform denoising of the data points by sort of projecting them on the unknown manifold while doing something else while I'm looking for this manifold. So what is a manifold? We have some data points, tau j, that are seated in a low dimensional space. We have some function f that project those points into high dimensional space. And we do not know what is the intrinsic dimension of the data themselves, and we don't know what f is. And on top of that, we even have some random noise, the EJs that were added to these points. And eventually what we observe are those points that we measured, PJ, sitting in high dimensional space with noise, and we wish to denoise the data. So if we formulate it in a mathematical way, we have a manifold that is not known, of d-dimensional, but is embedded in Rn. And we see some points that were sampled from the manifold itself. Those are the PJs. And we wish to denoise the manifold and reconstruct it reliably. And this is a very common problem. If we have a set or correction of images, it's very hard to denoise each image separately. For example, in the cryo-EM settings. But if we have a collection and we can use the underlying similarities and dissimilarities between the point, we can denoise all the set altogether. So that's what we are aiming for. We are looking, we have originally those P tilde that are sampled from the manifold, some random noise with bound, that is bounded the EJs are added to M, and we are observing those PJs that are noise with that are points with noise. And now we would like to reconstruct those the original manifold in terms of find a new representation, new set of points that we will call from now on QI, that will be sitting on the unknown manifold and denoise the original data. So we have P, we are looking for Q, that will be the optimal and in terms of denoising the data. And this problem was studied for a long time. There were a lot of methods that were suggested. Most of them had hard time with dealing with noisy data. Some of them were able to deal with noisy data, but assumed something about the data itself. And when we started working about that with David Levin, we decided that it's a good problem to dive into. And we solved it by introducing an optimization function that consists out of two things. And I'll explain shortly what are we talking about. So the optimization function basically tells us the following thing. We have unknown manifold and we have those PJ points. We are looking for the optimal QI that will be sitting on the manifold itself, but we do not know where should we locate them. So we are basically performing some optimization on the location of the QIs. So for each QI, we are looking on the neighborhood PJs that exist out there. And this is the reason why we have this Gaussian weight Wij. This is the support that will be looking around it. For each QI, we are performing weighted average on the QJs near it and finding the optimal location for the QI. So we're kind of performing K local mins on each QI, and eventually we will be happy if we are able to reconstruct the manifold. The second term that we see here, the lambda and sum of W eta distances between QI and QI primes comes in the situation where two QIs are getting too close to each other. QI and QI prime. If they're getting too close to each other, then we have some kind of penalty term in terms of this eta that will repulse them from one another in order to reconstruct the entire manifold that we have while doing the optimization. So from the one side, we are trying to stay as close as possible to the noisy data, we're averaging them. But from the other side, we are trying to reconstruct the entire manifold. And we have those Gaussian weights that have the support, and it's a long debate how to choose the optimal support here. And we have some analysis that I will not be describing how to optimally choose the H for the first term and H for the second term. They are a bit different. How to measure distances when we have noise. But eventually, once we are able to solve all those questions, we have this optimization function, which is non-convex, which will do a lot of headache to us in the future. And we wish to solve that. So how do we solve an optimization problem? So before diving into that, I just mentioned the first term is the attraction force that kind of keeps the points close to the manifold, and the second one is repulsion.
Sorry.
Yes.
So, do you have any assumption on the manifold kind of geometry? Do you have a smoothness or anything like that?
No, we don't have any assumptions. When we approve the approximation order, we assume that the manifold is smooth, but when, in the global sense, we do not have any assumption.
Thanks.
And we'll solve it with gradient descent iterations. So we compute gradient of our optimization function, which is a little bit nasty, but eventually it's just, we have another question.
Yeah, how is lambda chosen?
Lambda, it's, I will answer it in just in a minute in the next slide. So eventually it's some kind of weight between the points QI and PJ. And the alpha here is represents the weight that is related to each PJ. Where should we prefer to go? The beta is also the same. It's kind of a weight that represents the weight for each QI prime. And how are those parameters chosen? So there's several things that we need to discuss. How is the lambda chosen? So the lambda are balancing parameters that balance the first term and the second term. And we will choose them in the first iteration to guarantee that the norm of the two terms is balanced. So if we look on the two terms here, we are looking on the norm of the first term and the second term, and we are choosing lambda I in the first iteration that will guarantee that we are in the same scale in both of the terms, staying close to the manifold and spreading out. The gamma here is chosen based on the proposition by Barzilai and Brownie that it reflects the local curvature, and it tells us, if we look on the intuition what's going on here, I'll not go into details, but it tells us if the curvature is high, we will perform shorter steps. If the curvature is low, then we'll perform bigger steps in our gradient descent, which is logical. And now if we summarize all the algorithm here, so we have those PJ points that are the original settings, and here we have an example where the PJs were sampled from this cylinder. Those are the green points. We initialize the QIs in the first iteration by random sampling or sampling from a certain area on the manifold, and we wish to find the QIs that will both represent the manifold, but also will denoise it. And we will basically run these gradient descent iterations. And if I click on the video here, here's a good simulation that each time each QI progresses to its optimal location right now in the K iteration. And once we progress, we eventually aim at fulfilling the two terms that we will denoise the data set, but also find the representation of the entire manifold. So that's what we are doing. And now you say, okay, that's really nice. The example looks great, but what about the theoretical analysis? So we did some work about the theoretical properties of this optimization function. It was not really straightforward since this is non-convex function and there is no guarantee that it will indeed converge with the gradient descent. So we had to work a little bit hard to show that we will converge almost surely to a local minimizer. And just to give you a taste how the proof goes. So what we have here is some kind of Gaussian multiplied by distance from Pj to Qi. So the Gaussian, we know that it's a decaying function, and it's eventually, we can look on it, something that approximates a final support. So if we rewrite this optimization in a matrix form, we will have some kind of block matrix that is dependent on the support of the Gaussian. And if we look on the conditions that were proposed in the theorem by Lee, Schmidowicz, Jordan, Recht in 2060 that said that non-convex function will converge almost surely if you're able to bound the eigenvalues of the Hessian, as well as the minimal eigenvalue will be negative. So we worked really hard to show that the block matrix that we have here, the Hessian of it, we can split it into two. One is a matrix that with a bounded support, and some matrix that contained all the tails of the Gaussians. We showed for each one of them that we can indeed bound the eigenvalues and that the minimal eigenvalue is negative. And eventually we use the theorem to show that we will converge to something almost surely. We also showed that if the original manifold is smooth, we are converging to O of H square approximation order, where H is the field distance, which is the representative distance between the points. That also was very interesting. We showed also that indeed, as expected, the end result, the QI that we converge to, is uniformly distributed on the manifold, and we had to work a little bit hard for that. We can bound the number of iterations that we will need to run, and that depends on the starting point. And as you saw before, if we start far away from the optimal, we will need to run more iterations, while if we start from random sampling, and we will converge quite fast. And also we were able to say something about the complexity of the algorithm. So we were quite happy about those results. And we decided to run it on some numerical examples. we had to run it because we have to evaluate something about on a ground truth example. So the first example that we ran was one-dimensional manifold. In order to make it a little bit harder, we did some tricks. So the one-dimensional manifold is a manifold of some alphas, that we sampled randomly. We constructed the rotation matrix from that, which is a 2x2 matrix. We embedded it by flattening and embedded to R60 eventually. And in order to make it non-trivial, we multiply it by some matrix A that is normally distributed between 0 and 1. So we embedded our data points with this A and added some bounded noise, where the noise had a uniform distribution between 0.2, minus 0.2 and 0.2. And this is the original settings of the problem that we see. Original alpha are represented by the P points are represented by the green. We subsampled the Qs. We are aiming to reconstruct the original circle without any noise, the blue one. And once we apply the manifold reconstruction, you can see that the red point, the Q, are nicely now distributed around the manifold and reconstruct the entire manifold with some kind of evenly distributed. We applied it to other examples, for example, on the cone, and reconstructed it as well, that we embedded in the same way in R60. Another nice example is a 6-dimensional cylinder, which is a higher dimensional manifold that we played with, and again, embedded in R60, reconstructed it, and also measured with our ground truth how close are we to uniformly sampling this cylinder. This is a cutoff of only 3 coordinates of the cylinder, but it gives you the kind of the feeling how it works in terms of this method. We applied it to this manifold of ellipses, where each ellipse was sampled from a manifold with different axes, and some Gaussian noise was added to it. And we showed that we indeed are cleaning the pictures themselves with the SNR that decreased from 15 dB to 36 dB. We played a little bit more with the amount of noise that we can tolerate with some numerical examples, and we're able to show that even with 15% of noise added to the data from the magnitude of the data, we are still in a reasonable relative error. This was a numerical example that we did on the cylinders, that we added more and more noise. And the reason for that is because basically we are performing some K L1 medians, which are robust to 50% of noise in the data. So we were quite happy with that.
Yeah, that's a question.
Yes.
So no matter what's your initial distribution for the data, you can always get the uniform distribution for the resulting one.
Can you?
I mean, no matter what's the initial input data for the distribution, you can always get the resulting uniform distribution for the.
We will get a uniform distribution on the manifold, yeah.
I see.
It will just take longer if we start from not a non-optimal starting point, but it will converge faster if we are already close to that. More questions?
Is this true only for large lambda, or does it depend on how big lambda is?
Uh,
That's the term that's causing it to be uniform, right?
the lambda?
Repulsion term, like there's the lambda in front
Oh.
of repulsion.
The lambdas are only balanced in the 2 terms. They are not, I don't know if they're related to the distribution itself. We have the H in the support of the Gaussian that is related to the density.
If you turned off the repulsion, it wouldn't be uniform.
Yeah, it would not be uniform, definitely. And I also some numerical examples that it's not working. Yeah. So that one is guaranteeing that we will indeed have something uniform. And we decided to approach other problems that related to manifold and operations of manifolds. So we played a little bit of function approximation on manifolds. If you think about it, it's just a generalization of our problem, where we have function values that also are contaminated with noise, and we wish to denoise both the function and both the values on the manifold. We also proposed an extension of our method by adding additional term to deal with the following problem, that if we have a missing data that was not sampled originally from God knows why, because maybe there was occlusion or something else, the method that I showed you before will, because of the constraint of staying close to the P points themselves, will not reconstruct the point inside the hole that exists here. So we propose another term that is basically responsible for propagating some data points from the boundary of such holes into the hole itself and reconstructing the information inside the hole. And we have a bunch of more things that we are still aiming to do, but that was the free thing that we did. And that was basically the work that I did with David, and then I came to Duke and I started talking with Ingrid Debussy, and she said, oh, we are dealing with this project of lemurs and primates for a long time and you should be involved. And always it's a problem for me to say no, so here I am, 3 years later, dealing with the orthodontical problems of lemurs and monkeys. So the problem is the following. The evolutionary biology people are scanning those surfaces and that are originating from teeth of lemurs and monkeys. And the scans are not perfect. They have holes. They're contaminated with noise. And I just told you that I have this method that I can clean the data, but also reconstruct the information inside the holes. So I started applying that on the teeth data set that we have. This is a real tooth, which I did an artificial hole here just to estimate the error rate that we have. And I applied my reconstruction algorithm. And the tooth is a low-dimensional manifold. It's a surface. And this is the reconstructed result. If we zoom in, we see that it's reconstructed quite nicely. So we are still negotiating with the biologists to add this to their common flow, which is currently all of those fixing and denoising is done by undergraduate students and is quite time consuming. The reason why they don't want to do that automatically, because they're saying it works manually, why to do something automatically? So maybe one day they will agree. So what we have now is one surface that we reconstructed that is a tooth. But we can do it for more surfaces and even more and even more. As many surfaces that we have. So we were talking about manifold. So this is a manifold. Manifold that each data point is a surface, is a shape that we want to deal with. And if before we didn't, or we kind of closed our eyes and didn't ask what are the points that are sitting on our manifolds, now we will ask ourselves, what are they and how can we use this knowledge to improve our manifold learning algorithm? So the problem is still the same. We have some manifold, we have those points that were called previously PJs, now let's call them SI, that are basically shapes. They can be either some images or some surfaces. And we wish to study this manifold of those shapes and say something about how similar they are, how different, and something about the geometry of the manifold. So this is a joint project with Ingrid Shanshan that is in Denmark, two undergraduate students, Ray and Alex. Ray is now in Washington and Alex moved to his PhD to UNC. Doug Boyer from the evolutionary department, and Tinran Gao that started this research. And basically he is the one that proposed the random walks on the shape spaces. And we'll see where this research goes today. So let's revise for a minute what's diffusion maps means. We talked about reconstructing the manifold, but now we are moving to a different thing that is basically a dimensional reduction of the data points at hand, those xi's. And what we are doing is we are tailoring the global geometry by diffusing locally. So I told you already before that we are looking for each point here, and we are looking on some diffusion time t. We are diffusing each point during this diffusion time, and we have those neighborhoods that coincide, and we can perform random walk locally in each neighborhood and tailor the global geometry. And that's what diffusion matrix is all about. Once we have the diffusion matrix, we find the eigen decomposition and use the dominant eigenvectors to embed the data into a low-dimensional space and project it. And that's what they did with, Tinrat did eventually in his thesis with those shapes. So he took the data set where each point is a shape. I will not go into details. What is the distance that they used and how did they align the shapes? It's a long story, but eventually he projected the entire collection of the shapes to this three-dimensional space where each point here is a surface. And if we go back and ask the biologists, what are the species that we are talking about? So, and color each point by the species, we see that they kind of cluster nicely based on the species, but if we would ask to do it automatically, I'm not sure that we would cluster and draw the line between those two here and those two here. So can we propose something better than what we already have in the diffusion map? So the answer is yes. So until now, we used only the distances between the surfaces. Like somehow we compare one surface to another, and we have those distances, but what we didn't use is the correspondence maps between the surfaces. And what do I mean by correspondence map? So we not only have distances of how similar this surface is, but if I can ask the biologist to give me points on one surface that comes in correspondence to other points on the other surface, I'll be able to define some parallel transport between those two surfaces. And that's what we will do. So if I'm asking and they can give it to the finite data set that we have and those correspondence, then maybe we can use and improve the diffusion process. And what do I mean improve the diffusion process? So I wish to define a different diffusion, and I'll tell you in a minute how does it go, that will use this information of the parallel transfer. So if before I was working only on those points on the manifold, now I wish to incorporate the information of the parallel transfer. For that, I will need some tools from differential geometry, and I'll just add here 2 slides, just for the sake of remind you all what they are. So, and I will explain that on the example of this cylinder. So if we have a point P, X, and Y, it can be represented as a point on this cross section, on one of the cross sections that we will take, for example, S1 of the cylinder as a projection on the S1, as well as a point on the line that passes through that point and the S1. And if we do it in the notation of differential geometry, so S1 is the base manifold and R is the fiber. And we can look on a collection of those fibers that are passing from this base manifold. And now we have a mapping that goes from one point to our base manifold S1. This is a mapping that takes a pair XY and returns us X on the base manifold, and we have the inverse mapping that gives us not one point, but the entire fiber, the Rx. We can do it for any point, and basically the fiber bundle is the triplet of those total manifold, base manifold, fibers, and pi, which is the mapping between the total manifold to the base. So now, if we go back to our structure, we have those shapes. The base space, the S1 that we talked about before, is the shape space. And the fibers are the generalization of those surfaces. So those are the fibers, the R's that we were looking about before. So what we wish to do is use the parallel transport as both the distances between those surfaces to perform a better manifold learning. So if diffusion would diffuse only to surfaces that look alike the current surface based on the distance that we defined, now we wish to use the local geometry, and it kind of makes sense if you think about if this point is located on a cusp of this tooth. It's reasonable that it will be only diffused to a point that is sitting on the same cusp on the other tooth as well. And if the corresponding point is not sitting on a cusp, I will not diffuse them. So that's basically the intuition behind what I'll be doing. So I have two surfaces, SL and SK, which are a collection of points there. And it comes with those parallel transport, which are P from K to L. And I'll define some distance based on the surfaces and also based on the points and their neighborhoods. So now if we go one step back to the classical diffusion model where we diffuse each point with diffusion time t, we will define now how do we perform the diffusion now. So the first thing we will do, we will replicate what we already know. We will diffuse each surface K to surfaces that are L that are in the diffusion time tau, we'll call it tau 2. So we will move to all the neighborhoods surfaces that we have. But that's not the end. I already told you we have the additional information of the parallel transport. And what does it mean? So what I will do is not only I will look for a similar surface, but I also look for similar neighborhoods on the surfaces themselves. So I look for neighborhoods around each point, and I'll use the parallel transport that I have here, and I'll look for points that are similar in the same neighborhoods with respect to some diffusion tau 1. Since it's not symmetric, I will do the same thing vice versa and do some kind of averaging between them. And that's how I will do that. So I'm no longer diffusing just between different surfaces, but I'm also adding additional constraint and diffusing on neighborhoods that are looking in the same way. So this is what we call the horizontal diffusion map, or in short, the HDM that were proposed by Tin-Ran Gao in 2021 in his PhD thesis. And yeah, so this is diffusion on the base manifold on what we call the S1, and this is the diffusion on the fibers themselves. And if we look on the diffusion matrix, so if we had diffusion between different data points, this is a picture from the original paper by Koifman. Each row here represents a point in Rn, and we look on the diffusion of each point to other ones, and we order this so the points nicely, so it will look nicely based on the similarity between the points. So we'll see that it's kind of a block matrix, or maybe block diagonal. What do we have in our horizontal diffusion map? So we have a block matrix that each block is a tooth. Each point, each row here is basically a point on the tooth itself. So we wish to compare both the points, both the teeth themselves, the surfaces. This is the D that we have here in the first place, as well as the neighborhood. So each entry here is a point, and we will see how it corresponds, what is the similarity of the point to other points in the projection. We will do the same thing as we do it in the classical diffusion map. We will calculate the eigenvectors and eigenvalues, project the data to the dominant eigenvalues and vector areas. Is there any question? And now we have different settings. So if before we projected each point, a surface, to a point in R3, what we are doing now, we are projecting each surface to a surface while preserving the local geometry. So, for example, this surface will be projected to this collection of points. This surface will project to this one, and so on and so forth. If we combine them in one place, will result in something like that. The color coding basically tells us that it comes from different teeth. But what is interesting that a certain point that is in correspondence with other points on the TIFF will be projected to the same location in the embedded space, what we call the template space. So now we do not lose the local geometries, and we can study what's going on the TIFF themselves in this joint projected space. We can look how the variation changes and other things like that. We can define, of course, some diffusion distance based on the projection that we did. And this is some of the things that we can do. We can perform some kind of clustering on the distances in this HDM space. That's what they did here. And those ones are a little bit better than the diffusion map distances that we had before. We can do the clustering, and this is the automated cluster that they actually find based on the similarity in this HDM space. We can perform the clustering in the template space itself here. So we can cluster it to K clusters and see what are the correspondence location on the tooth and color code it and see that what is the biological meaning of each such area. And it actually surprised the biologists that they were, what kind of surprised them that the mapping is not area preserving, and some biological areas here that they thought correspond to a bigger or smaller area here, and they had to reevaluate their biological understanding of that. And what we are doing now with Alex is basically using the template space definition to improve the registration of those TIFF. And we are doing it by optimization on the template space itself. I'll not go into details because that's a different project that is too long to describe right now. So what the future holds with respect to this HDM, we still need to understand how to diffuse tau1 and to define the tau1 and tau2 parameters. We have a hatch how to do that. We need to study the properties of this fiber bundle kernel. We still want to play a little bit with different kernels, see how they influence the theoretical analysis. We want to perform spectral analysis on the horizontal diffusion and spectral convergence. We want to play with in control settings with different amounts of noise and have some theoretical understanding of how the noise influence on the reconstruction. The other question is, if we have two manifolds, that means that we have a product of manifolds, how do we diffuse on both of them together using this HDM? And how do we perform diffusion with incomplete surfaces? That is basically interesting. So I hope that by now you kind of get a feeling how those interdisciplinary projects work. We require the data, which can be a long process. And eventually we forget where the data came from. We play only with similarities, with global and local similarities of those data points, and try to understand something about the global picture where the experts can understand and add to their knowledge. So we talked a lot about this project, and I want to add a few more things about this project that was going on for 10 years, and I was really excited about it when it was going on, and I'm still excited. So the problem in hand that we wish to analyze ancient texts by comparing different shapes, which are letters. So I already told you, and I wish to answer this question of the mystery of literacy in 600 BCE with mathematical tools. That we can tailor the global geometry by looking on that locally. So we will denoise the data, choose the right distance that correspond to our project, need the geometry locally to better understand the global geometry, answer broader questions, publish and get famous. We acquired images of those inscriptions. I felt like an Indiana Jones in a movie, going to those basements and asking for this specific inscription. Can I take a picture of it? We reconstructed and created binarization of those letters by modeling the letters with the B-splines. It was challenging as well. Later, we extracted some features that can use for the comparison of those letters. And eventually, we asked ourselves whether two inscriptions were written by the same person or not, whether the two distributions of letters that exist from one inscription and from the other one were sampled from one distribution or not. And what we wish to answer is how many people were literate enough to write the corpus at hand. So we did it on one corpus of Arad inscriptions from 600 BCE. They are from Kingdom of Judah. They relate to the last months of this fort that existed in the desert before the destruction by some Babylonians. We examined 18 texts, and we find out after our shape analysis that there were at least 6 texts, and that also all the people in the chain of administrative command were literate enough based on textual evidence. We performed the same analysis on shapes of those letters on 8th century corpus from Kingdom of Israel. They were written along 7 years of this kind of temple that existed out there. We know that by the date they have written on the inscriptions. We examined 31 inscriptions that were legible enough, and we, after a lot of work, we can state that the maximum likelihood estimate here is 2, by only comparison the distribution of those shapes. And that the 2 hands are contemporaneous, meaning that we cannot cluster them by years. They were 2 people sitting out there. So I already said that we want to summarize the result and get famous. So we published that in PNAS and got famous. It appeared in the New York Times in above the fold front page, our research. We continued doing more research on the other corpus, and it also was published on +1. We also find out a new inscription that no one knew that existed out there with mathematical tools. And if you want to learn more about this exciting project, you can click on the link here or look for nuclear ostraca. Ostraca are those inscriptions. Nuclear because I was sitting for many years in a nuclear lab. So if you turn off the lights here, I will glow probably. And thank you for your attention, for listening on my presentation on the manifold inferring, and also a little bit on those fascinating inscriptions. And I hope that you have the feeling that applied math can really change the world in so many perspectives, just by tailoring those little dots and trying to understand the global picture. So thank you for your attention. If you have any questions, I will be more than happy to answer them.
Are there any questions here? There are a couple on Zoom I can read out. So on Zoom, in the manifold section, so this is back in the first part of the talk. If the manifold's rough, do you have strategies to converge to a measure that's concentrated where the manifold's rough as opposed to uniform? I think it kind of means like if it's, if it's very flat somewhere, you might not want many points there, but if there's some rough behavior that you have to capture with more points, you might want.
Yeah, so currently we are spreading and reconstructing it uniformly, but we can definitely add additional weights to guarantee that. So at certain points that there's not a lot of information that will sample it more sparsely, but while in other location we are sample it or more densely. A good example is just in computer graphics, if you have a hand that probably you don't want to sample this area densely, but here you have so many changes that are happening. So we are still considering how to incorporate a weight that will sample more densely here. So this is the future work that we'll be doing. Yeah. More questions?
Another one on Zoom, which is maybe more broad. So how much can experts from the fields tell us about metrics? I think like first part of your talk.
How can they tell us about metrics? So they usually have their own understanding on what the solution is and what is the problem, and they learn and acquired so much information during the years that they were doing it, but they do not know anything about math, usually. So the problem is to understand and infer somehow their gut feeling, their kind of expertise, and translate it into something that we can actually measure with metrics that are in Euclidean space. This is quite a challenge, but I think that it's possible if you worked with such interdisciplinary people before and you know what questions to ask and what information do you need in order to do that. So I think that it's an art by itself, but it's possible. Having said that, it's not always the optimal thing to do because they kind of have a bias. And in the project of those inscriptions, we asked the people, what are the indicative letters that you use for the separation between inscriptions? And they told us, we are using this and that letter. And we decided not to use those letters at all. We decided to use some random other letters that we had enough statistical analysis, and based on those that the archaeologists said, there is no way you're going to separate those inscriptions. We were able to do that. So sometimes it's good to incorporate data from the experts, but sometimes it's kind of a bias that you want to avoid. So it's kind of a very narrow bridge that you want to go very carefully. More questions here?
Yeah, does this work if you do, like, instead of surfaces, if you do images as your manifolds in your manifold? That makes sense?
It will work as well as the surfaces. There's no constraint as long as you have some kind of alignment between them.
So like if you had like a collection of images in a similar location and you're trying to map similarity between.
Yeah, you can definitely do that.
How does this work for objects that aren't very rigid and have a clear boundary? I'm thinking about clouds, like if you were trying to replicate a cloud shape, the boundary of the cloud's really fuzzy,
Yeah.
but you still have regions of like very dense things versus like very sparse things. I still would think though that a model kind of like the one presented here in the first part of the talk would model the cloud really uniformly, even though its density doesn't.
Yeah.
Is that the case or no?
It's an interesting question. It's interesting even how to model such problems, because if they kind of, the boundaries are not really like well defined, so how do we approach that? We haven't thought about those questions, and maybe it's something that is interesting to look for. What questions?
So for your handwriting work, have you tested it on any experimentally generated texts?
Yes, that's a good question. Yes, we did. We had to do that before claiming something about the historical settings. So we get at that point when we started in 2010, there were no data set of modern ground texts that had also ground truth, and we had to collect them manually with basically going through the university and asking people to write us a bunch of letters. We segmented them, we performed our analysis, we ended up with an accuracy of 98% on modern data sets, and with I think 2 or 4% for false positive. So the results were quite good, and that's kind of gave us the green light to go forward with the ancient handwriting. Otherwise, we wouldn't naturally go forward and claim what we claimed. But that's a good question.
There's
also another question
I
here.
want to understand better on the, I think you call them parallel transport. So what would happen if you have two images of the teeth, for example?
Yeah.
If a tooth is exactly the same shape but twice as large, what's going to happen to the mapped manifold?
It will map the corresponding points from one tooth to another. It disregards the scale of the teeth itself. It's kind of a mapping between points. So it's
Okay, so the scale is
Yeah.
actually just canceling out.
Yeah.
Okay, perfect, thank you.
On Zoom, thanks for the wonderful talk. Can you say something about the manifold learning work? Can it be extended to spatial temporal data that has some time?
Oh, that's an interesting question. Yeah. So at some point I started thinking about what happens if we have a time series of manifolds and we wish to reconstruct the manifolds that as it evolve. Eventually I ended up at Duke and I didn't progress with this work, so basically it's still, I think, open, but I think that there is no constraint in applying what I call the manifold reconstruction and denoising on a time series and seeing how it works. Maybe with the use of parallel transport, maybe it will be also something that we can consider, but it's a good question, yeah. Something that we definitely consider at some point.
And also this method with random walks in shape space, all the shapes, at least in your teeth example, all the shapes are pretty similar and there are
Right.
minor changes to them.
Right.
Are there settings where that wouldn't be the case, where there would be drastic differences between the shapes?
Uh,
Have you thought about that?
So the teeth problem is quite unique because the common tools from computer graphics cannot be applied to that because of the small variation in the tooth themselves. We can definitely apply to shapes that have a larger variability, and it will be interesting to see how it goes, but there's no restriction on that, definitely. But the method itself was designed to deal with those small variation between surface and surface.
So for the teeth parallel transport, could you add like a term or something that would like perform a graph cut to only register a certain part of one tooth to a certain part of another tooth, say if like half a tooth was missing?
Yeah, I think that's what is gonna happen in the future work that I mentioned, that how we are going to like deal with partial teeth, because this is, I think, most of the data, not only in the tooth, but usually in the bones as well, is very partial. And can we define something that is have this partial parallel transport? And that's something that we'll probably look at in the future again.
Any other questions?
And if you have any questions, I'll be more than happy to answer them right now.